So good morning. My name is Maarten Sierhuis. I'm the director of the Nissan Research Center in Silicon Valley, and I want to thank the organizers of this conference to invite me to come and talk to you. I have a little bit of different title, but it's essentially I'm going to talk about how we use autonomous driving to create new mobility applications. I think everybody here in this room by now has heard about autonomous vehicles driving on the road, and I'm going to explain to you a little bit about what we're doing in this area at Nissan, specifically in Silicon Valley, and also how we are collaborating with NASA Ames, right our neighbor down the road. So it should be some interesting work that we're doing with NASA. Okay, so let me first explain to you the roadmap for Nissan in autonomous driving. Actually, last year, Nissan introduced in Japan the first vehicle for Nissan that drives hands-free on the highway. It was the Serena. This year, actually, this week, I believe, I'll be in Las Vegas tomorrow, where Nissan is introducing what we call ProPilot in the United States. It's going to be on the Rogue, and the next one will be the new Leaf that is coming out very soon. This is what we call highway single-lane driving. That means that you're on the highway, you're in a lane, you can take your hands off the steering wheel, and the car will stay in the lane and it will drive itself. In traffic jam, it will stop and go as the cars are stopping and going in front of you. Now, this is all nice. This is, of course, not where we want to end. Where we want to end is to drive completely by ourselves. But we are taking a stepwise approach to get there. So the next version, which supposedly is coming out around 2018, which is next year, and then the system will be able to change lanes on the highway by itself. You can imagine that requires more perception around the car, because now you have to look to the back to see if a car is coming, and we have to figure out if there is enough room to safely switch lanes and pass a car in front of you. Okay, so that is coming around 2018, probably in the US. It will be 1 or 2 years later. Nissan always brings out its first releases in Japan, but you can expect this in the next couple of years. The next one, which is I should say that these first two, we in Silicon Valley have not participated in the development at all. Because why? Because it's simple. Right? And so we work on the hard stuff, is what I say. And so what we've been working on is the next version, which is driving hands-free in urban cities or in urban areas, which is off-highway. I say urban starts at the moment you take the exit on the highway. We start with urban driving. And why is that hard? I will try to explain to you a little later why that's hard. But basically, the complexity increases because we have more individuals on the road, be it humans, be it dogs, be it whatever you can imagine, bicyclists, motorcyclists, and everybody, as well as very difficult traffic situations. We delivered this in April of this year as so-called research out. So we have, as research organization, have delivered this to advanced engineering, where now Nissan is working on making this a product, which takes another 3 to 5 years, right? But I will show you the capability that we have right now of driving in urban areas. What we are focusing on next, I should then say that all these systems will be what we call eyes on. That means a driver is in the car, is behind the steering wheel, and is always the one that has to be paying attention and take over when the system cannot handle, right, the situation. So we call it eyes on. What we are working on now in research is eyes off. And we say that that will start somewhere in 2002X. That means somewhere in 2020s, we will deliver what we then call robo-cars. Cars that drive by itself where there are no drivers in the car. Right? So that is what the research part of Nissan is working on today. So let me first give you a little taste of what driving in urban areas is. So this is Mr. Ghosn in January in our office. Mr. Ghosn, the chairman of the Alliance, which is CEO of Renault and chairman of Nissan. And he is driving, he was the first CEO of a car company actually driving an autonomous vehicle. So he is now leaving our premises to drive in Mountain View, right? And so the car here is completely autonomous. It's driving by itself. As you can see, we do not have large sensors on the top like some other manufacturers and companies you have seen. It looks like a normal car, right? This is actually on the south side of NASA Ames, where we are located. And you will see in a moment that the car is driving downtown Mountain View here. You can see the human-machine interface there in the center. It's negotiating traffic lights, it's negotiating pedestrians, it's negotiating people crossing the road, etc. This is a research vehicle, so we're not claiming that we can handle all situations, and I'll get back to that in a moment. But the system is working pretty well. There are many issues that we are needing to solve, like localization, like more capable perception. And so let's look for a moment, what does it mean to have an autonomous system on board the car? So this is a high-level diagram of an autonomous software architecture that we have in the vehicle. We are building this architecture at Nissan in a way that we can plug and play different modules. So as perception gets better, we can put in a new perception system. Everything comes together. So I start on the left side where sensing comes in. So this is where the sensors are: LiDAR, radar, cameras, you name it, GPS, whatever we can get our hands on to get more information about the outside environment, we would like to get into the system. The perception module then creates an understanding of what we're seeing. We know that there is a pedestrian that we're tracking. We know that there is cars around. We know that there are maybe trucks, bicyclists, a tree, a traffic light, right? All these objects that we see in the environment, the perception system will put into what we call the world model. The world model is what it says. It is a model of the world. It has all the objects in it. It has all the information about the objects that we know. And so now you can see that as the perception gets better, we can get more information about the object. We have dynamic objects, that means pedestrians that are walking around, and we have static objects. For dynamic objects, we need to know what the direction is that the individual or the object is moving in. So if I'm moving this way, we have to have an idea of where this individual is going, where this object is progressing to. And we do this probabilistically, because if I go like this, what is the probability that I suddenly turn around and go the other way? These are the kind of things that the perception system and the world model is handling. Right? The a priori information is the maps that we're using in order to track these objects on a map, to know exactly the location of these objects. The ego state is where am I in respect to the map and in respect to the world. And here you can see that it's very difficult because maps are never accurate and the world is always different. So where am I exactly in the world is a really, really hard problem to solve. It's so hard that it's really still research, right? Because the GPS that we use is not accurate enough. We can put a $50,000 GPS on the vehicle and it's not accurate enough. At NASA Ames, there is the largest wind tunnel in the world that creates all kinds of havoc with GPS. right? So knowing exactly where you, in 5-centimeter accuracy, where you're on a road is not something that you can do easily with GPS. So we have to find all kinds of other tricks to make sure that we know exactly where the car is. This can be from following the lines that we see on the road and then corresponding the lines with what we know in the map. But if there is no lines on the road, which is obviously a lot in urban areas, this is not possible. If I'm driving down San Francisco, forget the lines, all right? There are no lines, there are potholes, that's about it. All right, so it's very hard to figure these kind of things out. The decision-making module is the most complex module. That's where everything comes together, where this car needs to make a decision. To make a decision, it needs to know what lane it's in, it needs to know where it needs to go, it needs to know what all the other objects are doing on the road. So this is continuously looking at all this information and figuring out what to do. And then the control of the vehicle is really the steering, the acceleration, the braking, etc. All right? So the interaction between decision-making and control is very important, because that's where the path, so the decision-making generates a path for the car to drive in the next 3 to 6 seconds in different levels, in different hierarchical plans, and then the control system has to make sure it can drive that path, right? If the system generates a path that the steering cannot handle, you can get into all kinds of trouble. So you can see that these modules all communicate with each other. Well, the system would actually be easier because, you know, autonomous system will be more predictable than humans, but we are not modeling the world in the sense that a child might walk differently than a grown-up person, or a mother with a child is different. No, that's not how we do it. So we don't distinguish between a car that's driven by a human versus a car that's driven by an autonomous system, right? We just look at this as an object in the world that has a certain history, right? We can track this object and we know where that object has been, and then we project where that object is going, right? And the trick is not to be always correct, because if you want to be correct always, you're going to just stay at home and never walk anywhere, right? That's when you're just make sure that. So you have to have this probabilistic, you know, and we have thresholds. Like if I know that this person is walking with 75% or 79%, right? How is that different from 67%? That doesn't make a lot of meaning. So we have to find tricks to deal with that. And it goes into all kinds of, you know, AI technologies to explain what, you know, how this works.
Just one related question. Is this assuming that somewhere during this period or in the future that there's also going to be kind of a network where all the cars are networked together and there's some kind of a network master control that's outside the vehicle?
So, you know, I will show you this in a moment. Yes. Okay. So this is all technology we're developing. It's nice. But what we want is a car that behaves socially in the world. We want socially acceptable driving, right? And what do I mean with that? Humans are social entities. We are the best autonomous systems that we know of. And we are social. We always communicate. We don't do things alone, right? And so we feel at Nissan that vehicles need to understand that they are a social entity in a social environment with multiple autonomous entities, and they need to be able to interact. And this is not just inside the vehicle, right, where people are sitting, and we need to develop services for these people that are in the car, but also, and people wanting to interact with the vehicle inside the car. But we also want to make social a concept that is about the outside of the vehicle. right? To understand what other road users are doing, right? And understand that people outside of the vehicle, not just drivers, also interact with the vehicle. Now, to make this a little bit more clear about what I mean with the outside, let me show you a little video. This is a 20-second video of a normal four-way stop intersection in a small town, Campbell, in California, near San Jose. Okay? And to really analyze what's going on in this video, we probably need an hour talking to each other what's going on. Right? But I want you to just look at this and realize what it means to drive on a road in the United States today. So I want you to first focus on that yellow circle where this pedestrian is walking. Oh, I probably have to. Okay, so the pedestrian is walking. Here comes this white vehicle that takes a right-hand turn. And watch what this vehicle is doing. It's inching up. Like, look at the other two vehicles that are fighting with each other. Who goes first? Right? Now you see the pedestrian running across. Now this other car goes first. Now, was he there first or not? Now watch the other two here. Her pulling her husband or her friend back, and the car, see the person waving to the couple? Right? This is 20 seconds. I mean, I already lost count how much communication was going on. Right? What I didn't even focus on was the father with two children driving on the wrong side of the road on their bicycles. Right? It's like in Europe, this father would be in jail. Right? So, you know, this is 20 seconds. A standard industry, not even complex in our vision, right? So imagine that one of these vehicles are an autonomous vehicle. So, I hope with this I show you, it's hard. It's a difficult problem to solve. What I say that this is human decision making, and we want cars that understand or maybe make decisions like a human. The human-like decision making is what we have now as a research topic for this year. And let me show you a small video, and this is at NASA Ames that we have been doing this testing, of how we try to mimic this human-like decision-making. And it's very subtle. And we have a group of social scientists, anthropologists and sociologists that are actually doing this research in trying to understand what human-like driving is about, what this socially acceptable driving is about. And they're coming up with concepts like creeping, piggybacking, these kind of concepts that we as humans are not even aware of what we're doing, when we're driving or when we are pedestrians. So, let me see if I have to. Yep, it drives. So here's just a three-way intersection at NASA Ames, and here the car comes almost simultaneously there. This is you're looking from the autonomous vehicle, and you saw the car creeping a little bit forward, right? And then moving, and it knows that the other car came there first, and so it had to wait. So this creeping behavior is a very human-like behavior to communicate who goes first, who goes next. So here is another one where you see the vehicle. They're waiting. You see the vehicle now. Now the vehicle wants to go first, and so but now this other car goes first, right? So but it started to creep, and now it says, okay, you guy wait there on the left. Right? And so we're now trying to make this general in complex situations. So here you will see an example with a pedestrian and cars in the same intersection. And what you don't see maybe yet, but there is a person standing there on the right-hand side next to the orange cone. And he is starting to fool the system a little bit. And now so it says, I'm going to go, and then it sees the pedestrian. So it slows down for the pedestrian. And then it waits, and when the pedestrian is gone, it goes. Right? Yes?
How do you know if they're following stops as opposed to stops where the trailer gets the right of way?
So it knows the rules of the road.
Why
Oh, so the stop signs are in the map, right? So it knows that it is a four-way stop intersection. So this is what we call high-definition maps. This is a whole topic in of itself about what does it mean to be a high-definition map. So Google Maps is not high definition, right? We need to have exact lanes. We need to know where the stop line's in, etc. Now, so this is what the information, the a priori information that we're having. So this is all nice and dandy, but then we get these kind of situations. All right? So I took these pictures myself in San Francisco. This is in the Mission. And it took me about 3 minutes to figure out what to do here as a human driver. Right? If you look closely, so first of all, there's a double yellow line, which I'm not allowed to cross. Right? There is a red light. By the way, I drive this intersection every day, so I know kind of how busy this intersection is. But these guys are standing, I couldn't go to the right, so I knew I had to go to the left. I knew at the moment was green, all kinds of cars were coming from the other side. I mean, it took me a long time to figure, there's nobody telling me what to do. I can't see in front of the car, is there a pedestrian or not? This is a tough situation. And then this one was 2 days later in Palo Alto, which was even worse. You know, I'm already driving on the wrong side of the road, having crossed the double line. And you see, you know, this guy is standing there with this sign. I'm not allowed to turn right. The light is red, and the person in front of me is driving through a red light. You know, so how are we going to make vehicles understand this kind of complex situation, right? So what we have developed together with NASA. So NASA, you know, uses teleoperation to operate vehicles, autonomous vehicles on Mars. Now they use 300 people to do this, and that's 300 to 1 is, actually 300 to 3 now maybe, right? But so that's not an economically viable solution for a car company. But this concept is what we started to collaborate on NASA. NASA does not joystick the robots on Mars. Right? They send plans to the robot that the robot then executes autonomously. So this collaboration has led to a system we call SAM, and I'll first, so we introduced this at CES this year in January, and I'll play you the video first, and then we'll talk a little bit about what SAM is about.
It's one small step for man, one
NASA is recognized as the pinnacle of human endeavor.
Columbia, this is Houston, AOS, over.
The technology NASA has developed for space exploration has benefited society for many, many years. This technology that then gets developed can be used for autonomous vehicles to solve problems that we face here on Earth. It will be impossible to have fully autonomous vehicles driving around without ever needing help. Any autonomous system is built by humans, for humans. The vehicles will have to interact with human beings. And to do that well, and to do that in any situation flawlessly, we have designed a system for seamless integration into human society.
SAM stands for Seamless Autonomous Mobility. And what it is it's a system of support for autonomous vehicles and for transportation systems.
It's like the air traffic controls thousands of airplanes in the air with pilots in the cockpit, and still we have humans at a distance controlling and observing the airspace.
SAM is going to help us accelerate getting autonomous vehicles on the road by helping us deal with really unexpected situations.
Several cameras, LiDAR technology, as well as many other onboard systems assess the situation and build a picture of the world based on the best parts of each sensor. That's what we call sensor fusion. That picture is transmitted to the mobility manager, who then paints a new path around the obstacle. The vehicle can then safely follow that path and continue on. Once this new path is set, artificial intelligence in the cloud will distribute this to all the other vehicles to solve the same problem without the human in the loop.
The next autonomous vehicle traveling down the same road will maneuver around the obstacle without any assistance from the mobility manager. However, SAM doesn't just solve problems. Its bigger purpose is to provide a complete system of seamless mobility. Eventually, the system will manage thousands of vehicles at once, developing the bigger ecosystem for autonomous mobility. Autonomous vehicles with onboard and cloud-based artificial intelligence and connected services will drive services like robo-taxi, robo-delivery, robo-shuttle, and robo-sharing. It's Nissan's intelligent integration. Seamless autonomous mobility for the right purpose, whenever and wherever a rider wants it. The partnership with NASA allows Nissan's intelligent mobility to safely overcome the technological hurdles as we prepare for a world where autonomous vehicles will transform society for all people.
So this is our research concept, and I'll show you a little bit more detail about what SAM is about. We started this about 3 years ago with NASA, and as I said, we demonstrated at CES in Las Vegas in January that we could operate 2 vehicles from CES with this SAM capability using some of NASA's technology. So as you said, or as I said in the video, where do we get this idea from? Well, the airspace. Right? The air traffic control centers in the United States, have air traffic controllers who are very trained and skilled human beings that are actually communicating with the pilots, to make the airspace work. Right? This is kind of the concept that we use to say, well, we need something similar for vehicles, and what we need is we need to have humans in the loop for edge cases that need human perception, where the system is not good enough yet to make decisions by itself. But humans can actually help the system make decisions. No fully autonomous system works without a human in the loop. That's what we are convinced about. That's what I'm convinced about. There is no autonomous system that we know of today that works completely by itself. And if it would be, the question is, do we really want to, right? Because humans really want a safety net with other humans in it. We don't like this idea of robots taking over the world without us having some sense of control over the robots, right? I'm going the wrong way. So SAM concept is to use teleoperation and the cloud where AI is running, where we can learn from the data that comes in to make new decisions, to help the humans, to make the cars more smart, right? And so that's what SAM is about. And I need to hurry up a little bit. So the idea is to have a mobility control center where mobility managers are personnel that are responsible for the safe and orderly and expeditiously flow of autonomous vehicles. This could be a robo-taxi service, a certain delivery service, a municipal service where you have a control center where a fleet of autonomous vehicles is monitored and controlled with humans in the loop. That's kind of our idea. And of course, we don't want to have 300 operators to one car. No, we want to turn this around. We want to say one operator can monitor and observe maybe 100 to 300 vehicles, right? So that would make it more efficient and doable. So really what we're about is about moving the AI that is just on the vehicle to a combination of AI on the vehicle, AI in the cloud, and human intelligence to help the system to operate flawlessly. What SAM is now today is we have software that we developed on the vehicle that integrates with the autonomous vehicle software. We use NASA technology for communicating over 4G. So all this communicating of all the LiDAR, all the radar, all the sensor data, video in real time through 4G communication to the cloud. And then we have 2 systems. One is the fleet management system, and the other one is the virtual reality teleoperation system that NASA has developed, and we work together to make this available for the autonomous vehicle. And I show you, well, the functions here, let me first explain the functions. So the SAM fleet supervision is done by the fleet management environment to see the status of the fleet, to know where the teleoperation zones are, with zones that we need teleoperations for, vehicles requesting help, historical information. You can imagine all kinds of information you need about managing a fleet. And then we have the vehicle supervision, that is a 3D virtual world where the system will be able, when a vehicle asks for help, the system will now stream all the vehicle data, all the sensors in real time. The operator can look at this and can help the system make decision, right? And then on the AV, we need to have software that communicates, right? Now the interesting part was the intelligence of the vehicle is now not only to know how to deal with a certain situation, it now needs to know what it doesn't know, right? The known unknowns, right? It needs to understand, oh, I can't handle this situation, I need to ask for help. That's different kind of knowledge than knowing how to drive, right? So we're not developing a male autonomous system, right? Because it would never ask for help. That was a joke. Yeah. Okay. So here you see the system working. You see here the car driving. It's asking. It's turned orange. It asks for help. The mobility manager clicks on it. It streams all the data from the vehicle in real time. He can look at the cameras. He can select what cameras from the car he wants to look at. So he sees the person standing there with the slow sign. He can now draw this path. Right? He draws a new lane to tell the vehicle it's okay to go over the double yellow line. Wait for my command. Right? He's adjusting it. He can see, he can communicate with the person outside. Maybe there is a screen, maybe there is some way of communicating. And then he can give the okay to the system, and the system autonomously drives this new path. Right? So if something comes from the other side, it will stop, it will wait, it will be autonomous. It's more that the supervisor gives guidance to the vehicle to, help it go on its way.
So question, think about flash weather scenario.
What kind of weather?
Weather. So a car is driving and there's flash freeze, okay? That until the car hits the black ice, it doesn't know when it's spinning out
Right.
off the road. So do you anticipate this network infrastructure anticipating on someone who's monitoring state New York or Alaska, storm, flash
Right.
freeze or snow squall? I mean, what's the front end to that before it goes orange and says hell? How much of that intelligence is getting in front of it?
Right. So let's first set expectations, right? This is research. We've been doing this for 3 years. The system works, right? We have a cloud. We don't have an HPC yet, but maybe we will need it sometime. We can stream data to the cloud in real time. That was our first research question. Can we stream this data, in real time? It's a lot of data to stream. I think there are 7 or 8 cameras on the vehicle, right? Plus LiDAR, to stream this over 4G, that in and of itself is not an easy task. This is just the interface when the car asks for help. Since we're in the cloud, we will integrate all kinds of other information that the mobility manager deals with. And to give you an example, if you talk about weather, yeah, of course, there are limitations that the car, if there's black ice on the road, and we know from weather report and traffic report that there's black ice, the fleet operator will probably not drive his or her autonomous vehicles on the road. The system will not operate, right? The car by itself will always have safety on it, right? So another part of the research that we're doing is about control. How do you control the car? How does the autonomous vehicle can drive better than a Formula One driver, right? So we have systems on the car that will always try to maintain safety and will be better at dealing with black ice than any human will ever be. But we won't drive with, if we know there's black guys on the road, we will probably say, let's stop the vehicles. Let's stop this robo-taxi service for a moment, and sorry, but you'll have to walk. So this is how we deal with weather. Sensor technology right now, dealing with ice and rain, we can drive in rain. As you saw in the first video, it was actually raining the day that we drove the CEO through Mountain View. But it was raining. So we actually use the NASA Ames weather report to know, when not to, just like pilots get a weather report and say, we can't fly anymore, we stop. We have a ground hold. We do the same thing, right? So these are the systems that we will have in place to deal with this. But the sensor technology right now cannot really deal a lot with fog, with heavy rain, with snow. It's still, at a level that the cars won't be able to drive. Yeah. Okay, I have many fingers. So this gentleman here.
So this is an amazing presentation, and it really brought it together for me to see what you guys are doing. But the thing I thought about, all the technology gives you competitive advantage for Nissan, but you're also expecting a lot of things to be there in the way of operational information. So is the automotive industry thinking about interoperability of things that you all need to share in the way versus what you want to do for your own competitive advantage?
This is a hard question. I mean, I've only been in the automotive world for 4 years. What I've found out is that there ain't no communication between automotive. They're fierce competitors. For SAM, we already so we're trying as a research group to say, you have to work. This has to be open. This has to be working with others. What I didn't talk to you about today is what we call the external HMI, is an example. So how does the vehicle communicate intent to the outside world, to the pedestrians? And we have a concept that we tested and we're doing, but if we use, purple lights and, red flashing lights, and Mercedes uses, green lights and yellow, that's not going to work, right? So we...
Same problem in HPC. We had interoperability for many years.
Yeah.
We all had to agree on standards. Those standards, then you create things that plug into it, I think.
Yeah, so NHTSA is supposed to help, in the National Highway, whatever the acronym stands for, is supposed to coordinate this, but it will take time, right? But for instance, with the external HMI, human-machine interaction, we are talking already. So my group, we've created a conference. And it was actually in San Francisco at the latest Autonomous Vehicle Symposium, where we had a workshop where we all came together, right? And we start discussing. The ISO standards will define that. For SAM, as I told you, we have a piece on the autonomous vehicle called SAM, what I call SAM AV. We are developing this in a way that is an open API. So other manufacturers of autonomous software can integrate SAM into their software, and then they could fit into our SAM cloud, right? So we from a research point of view, we certainly want to be open, because it is clear, just like the airlines, if we don't have an open system, everybody, it's everybody for themselves, and it's not going to work very well, and the services are not going to be as good as we want. Okay, next.
Hopefully this question will be quick. Back to your block diagram where you had sensing, decision making, and control.
All right.
What's the rate of refresh? How rapidly do you execute that over and over again?
Well, there's different speeds that we're working in, right? And I apologize. I don't know the exact numbers that we're talking about, but we're talking about 100 to 200 milliseconds for updating the world model. We're talking in the decision making. We have decision making going on in a hierarchical form. right? So there's decision-making that looks 10 seconds ahead. There's decision-making that looks, just like navigation system. If I leave San Francisco and I want to go to NASA Ames or NRCSV, it starts planning that route. So it's on an hour scale, right? But then at the lowest, so if we look 10 seconds out, then there is a system that plans 3 seconds out, or 6 seconds, then 3 seconds. And then what is happening now, right? And so we plan, I think at the lowest level, a path for 3 seconds. And we do this with about, in 300 milliseconds, it updates. So we plan 3 seconds out every 300 milliseconds. And so it generates a path, exactly a curvature on the road where the car needs to drive. And that then is and then you have in the control system, you have something that updates even faster, right? That tracks through all kinds of sensors in the wheel and the acceleration and the steering where the car is. So there is control loops that are going on between the decision making and between the perception and decision making. And it depends on where we are in the system, how often that happens. I mean, I don't know if I answer your question. But so think.
Not entirely, but we can talk offline.
But think about it. It's not going to be the lowest level, maybe 100 milliseconds update.
Susie?
Hi. I was very interested in your comments about halfway through when you were talking about the need for continued human interface, that people don't want this to just be completely robotic. And I was wondering what you envision, because I'm sure Nissan wants to have its own people monitoring its own cars. Every manufacturer will, and that doesn't seem to be sustainable. I mean, is there going to be something like the FAA with air traffic control type of scenarios or monitoring stations around the country? Or how do you think that human interaction to adjust the cars, as you were talking about these different blockages, and how will that work?
Yeah, I mean, I am not so sure. You say that Nissan wants to have their own control center. I'm not so sure that that's the case, because they're a car manufacturer. They don't have managed fleets. They sell cars to Hertz, and Hertz manages the fleet, right? Hertz has a fleet of rental cars. So maybe Hertz will be the one that has a fleet of rental cars that are autonomous, that it monitors.